So let's start week 4 session 2. In session 1 we have studied about the formula del Q by del T is equals to K into A into T1 minus T2 upon X, where we have assumed that the assumptions were the rod surface is totally covered well by non-conducting material and there is no heat transfer to the environment. Now suppose if the assumptions are wrong, let there is insufficient steady state conditions in the rod while transferring of heat and there is a non-uniform cross-sectional area, then the equation can also be applied to a thin layer of material which is perpendicular to flow of heat. Like a thin layer could be as thin as dx. So let dx equals to small thickness along the direction of heat flow and dt is equals to temperature difference across the layer of thickness dx. Thus the heat current through this cross section can be written as del Q by del T is equals to minus K into A into dt by dx, where dt by dx is called the temperature gradient and the negative sign indicates that dt by dx is negative along the direction of heat flow. Let us understand the concept using a numerical. A metal cube with a length of 20 cm is placed in a heater set at 100 degrees Celsius at one end of the cube. The temperature at the other end of the cube is 22 degrees Celsius. So the condition is there is a metal cube of length 20 cm of which its one end is placed on a heater and the heater is set at temperature 100 degrees Celsius. Thereby the one end of the metal cube temperature is 100 degrees Celsius, whereas the temperature of the other end is 22 degrees Celsius. Determine the heat flowing through the cube per second. Also consider the thermal conductivity of metal is equals to 385 watt per meter per degree Celsius. Here insulation covers all other surfaces. Listing out all the given things from the question, the first thing is edge length of the metal cube is 20 cm. I have denoted it the edge length by x. Since we use SI unit, thereby 20 cm needs to be converted into meter, where we already know that 1 meter is equals to 100 centimeters. Thereby 20 centimeter is equals to 0.2 meter. Further, the given conditions of the questions are temperature at one end of the cube is 100 degrees Celsius. We have denoted it by T1. Temperature at other end of the cube is 22 degrees Celsius. We have denoted it by T2. Under the things to be considered, it is also given that the thermal conductivity of the metal is 385 watt per meter per degree Celsius. Therefore, the area of cross section of cube can be written as square of the edge length. This has come from the basic mathematics, that area of the cube is square of the edge length. Here as we see, the edge length is 0.2 meters. So the area of cross section of cube would be square of 0.2 meters, that is 0.04 meter square. As we need to know the heat flow per second, thereby we are going to apply the formula of heat current, which is del Q by del T is equals to K into A into T1 minus T2 divided by X. Thereby K is the thermal conductivity of the metal, A is cross-sectional area of the material, T1 is temperature at one end, T2 is temperature at the other end, X is the length of the material. So therefore, putting the values to these equation, K is 385, A is 0.04 as we have just calculated, T1 is 100 degrees Celsius, T2 is 22 degrees Celsius and length of the cube given is 0.2 meters. Therefore, on simplifying this equation and solving it, we get the final answer as 6006 watts. That is, the heat flow per second is 6006 watt. So is the answer of the question. Further, we are going to study about thermal conductivities of various materials. In the following table, a few materials have been given that are in general use. The table shows the thermal conductivity of aluminium is 209, thermal conductivity of brass is 109, the thermal conductivity of copper is 385, the thermal conductivity of silver is 414, the thermal conductivity of steel is 46, the thermal conductivity of water is 0.585. The thermal conductivity of transformer oil is 0.176. The thermal conductivity of air is 0.0238. The thermal conductivity of brick is 0.711. The thermal conductivity of sugarcane fiber is 0.5. The thermal conductivity of wood of oak tree is 0.146. The thermal conductivity is denoted by the letter small k, where the unit of thermal conductivity is watt per meter per Kelvin. From this table, we can also figure out which are the good conductors and which are the bad conductors of heat. Since aluminium, brass, copper, silver have higher thermal conductivity as compared to water, transformer oil, air, and brick. Therefore, these can be said as good conductors of heat, like aluminium, brass, copper, silver are good conductors of heat, whereas water, transformer oil, air, brick, sugarcane fiber, these are bad conductors of heat. Next, we are going to study about thermal resistance. Thermal resistance can be defined mathematically as R is equals to X upon Ka, where R is the denotation of thermal resistance, X is the length of the conductor, K is equals to thermal conductivity of the conductor, and capital A is equals to area of cross section of the conductor. As heat current is equals to del Q by del T, then del Q by del T is equals to K into A into T1 minus T2 upon X. Also, as we put the equation 1 in the above equation, we would get the result as del Q by del T is equals to I is equals to T1 minus T2 upon R. We have considered I is equals to del Q by del T. And as we put equation 1 here in this heat current equation, we get the result T1 minus T2 upon R. Let's try an exercise to understand this more. Analyze the thermal resistance of a copper rod with a length of 30 centimeters and a cross section of 2.25 centimeter square. Consider the thermal conductivity of the copper rod equal to 385 watt per meter per degree Celsius. So the question says the length of the copper rod is 30 centimeter. We have write that in given as well. The given conditions are length of the copper rod is 30 centimeter and we have denoted the length by x. Also, we need to convert this 30 centimeter length into meters, which can be written as 0.3 meter. The cross-sectional area of the rod is 2.25 centimeter square as given in the question. Since we need to use the SI units, therefore we need to convert this a centimeter square thing into meter square. By applying the same conversion factor of 1 meter is equals to 100 centimeter, we would get the result of 2.25 centimeter square is equals to 0.000225 meter square. The thermal conductivity of copper is said to be considered as 385 watt per meter per degree Celsius. We have denoted it by small k. Thus, to find the thermal resistance, that is R, we have studied a formula called R equal to X upon Ka. X, K and A we have already denoted in the previous slide here in these given conditions. X is the length of the copper rod, A is the cross-sectional area of the rod, and K is thermal conductivity of copper. Thereby, R is equals to 0.3 upon 385 into 0.000225. What we have done, we have just put the numerical values to this on this equation, and on simplifying this numerical values, we get the value of thermal resistance as 3.463 per watt. So is the answer of our question. The next thing we are going to cover today is the series connection. That is, when two conductors are connected in series and heat transfer takes place between two conductors. To understand this, we need to consider a system where two conductor rods A and B are connected in series. This is a system where two conductor rods are connected in series. This is rod A and this is rod B. The free ends are kept at temperature T1 and T2, where T1 is greater than T2. As shown in the figure, the free ends, that is free end of A and free end of B, are kept at a temperature T1 and T2, where T1 is greater than T2. So the heat will flow from A to B because T1 is greater than T2. The temperature of T1 is larger than temperature of T2. Let the temperature of the junction of the two rods be T. So we have also considered the temperature at the junction of two rods be T. Thus, heat current through the rod A is I is equals to T1 minus T upon R1. How this equation has just come? We have studied the formula in the previous slides. Here we have studied I is equals to T1 minus T2 upon R, where T1 and T2 is the temperature at the ends and R is the thermal resistance of the material. Thereby, heat current through the rod A is I is equals to T1 minus T upon R1. T1 is the temperature at this open end of the rod, T is the temperature at the junction end of the rod, and R1 is the thermal conductivity of the rod A. Thus, simplifying this equation, we get T1 minus T is equals to R1 into I, as R1 is shifted to left hand side. We denote this equation as equation 1. Further, the heat current through the rod B is I is equals to T minus T2 upon R2. Since T is the temperature at one end of the rod B and T2 is the temperature at the open end of the rod B. Therefore, we have written T minus T2 and R2 is the thermal resistance of the rod B. On simplifying this equation and taking R2 on the left hand side, we get the result as T minus T2 is equals to R2 into 1 into I. Let's suppose we denote this as equation 2. Thereby, on addition of equation 1 and equation 2, we get the following results. That is, T1 minus T2 is equals to R1 plus R2 into I. Or we can write that I is equals to T1 minus T2 upon R1 plus R2. As a result, the two rods are equivalent to a single rod of thermal resistance. Thereby, R equivalent can be written as R1 plus R2, where R1 was the thermal resistance of rod 1, that is rod A, and R2 was thermal resistance of rod B, that is rod 2. So equivalent resistance in case of series connection would be R1 plus R2. If n number of rods are connected in series, the equivalent thermal resistance is given by R equivalent is equals to R1 plus R2 plus R3 plus dash 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 plus Rn, where Rn is the resistance of nth number of rod. The next thing we are going to learn is parallel connection. For understanding parallel connection, we have to consider a system where the conductor rods A and B are connected in parallel. Let's see in the picture. This is the system where two rods, conductor A and conductor B, are connected in parallel to each other. A temperature difference of T1 and T2 is maintained between the free ends. Thus, T1 is the temperature at one end, T2 is the temperature at the other end, and this temperature difference has been maintained at both ends. Therefore, the heat current passing through the rod A is given as IA is equals to T1 minus T2 upon R1, where IA is the heat current in particular passing from the rod A. T1 and T2 are the temperature of the ends of rod A, and R1 is the resistance of rod A, thermal resistance of rod A. So heat current of rod A is given by T1 minus T2 divided by R1. Also, the heat current passing through rod B is given by IB is equals to T1 minus T2 divided by R2. Since IB is the heat current passing through rod B, T1 and T2 is the temperatures maintained at the ends of the rod B. T1 is at this end, T2 is at this end, and R2 is the thermal resistance offered by the rod B. Thus, the total heat current flowing from the temperature T1 to T2 is I is equals to IA plus IB, where we are going to put the equations of IA and IB. Thus, in filling up the equations of IA and IB on this equation we would get following results. I is equals to T1 minus T2 upon 1 upon R equivalence, where R equivalent is equals to 1 upon R1 plus 1 upon R2. Let me explain this again. When we have to put the equation of IA first. The equation of IA can be read from the previous slide, that is T1 minus T2 upon R1. We would place this equation here, T1 minus T2 upon R1. Similarly, at IB, we would place this equation T1 minus T2 upon R2. Further, as we see, T1 minus T2 component common in both the equation, so we would take common as T1 minus T2 and let sum up 1 upon R1 plus 1 upon R2, which could be rather written as R equivalence. Therefore, I is equals to T1 minus T2 divided by R equivalence. Here, 1 upon R equivalence is equals to 1 upon R1 plus 1 upon R2, as I have mentioned here. Further, if there are n number of conductors connected in parallel, then R equivalent of the system would be 1 upon R1 plus 1 upon R2 plus dash 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 plus 1 upon Rn, where Rn would be the thermal resistance offered by the nth conductor. Let's try to understand this concept of series of conductor and parallel of conductor through an exercise. The question says, two bars of copper and steel of length 75 cm and 125 cm respectively are connected in series such that the temperature at one end of the copper is 100 degrees Celsius and temperature at other end of the steel rod is 0 degrees Celsius. Let us understand the picture first. Two rods are connected in series. This is copper rod, this is steel rod. The open end of the copper rod has a temperature of 100 degrees Celsius and the open end of the steel rod has a temperature of 0 degrees Celsius. Also, it is mentioned that length of copper rod is equals to 75 centimeter, whereas the length of the steel rod is equals to 125 centimeter. Further, let's see what the question says. The diameter of both the bars are 3 centimeter. Determine the junction temperature of two rods. So, the other informations that has been provided in the question are: the diameter of the rod are 3 centimeter, and we have to find out the junction temperature between the two rods. Consider the thermal conductivity of copper is equals to 386 watt per meter per degree Celsius. Also to consider, thermal conductivity of steel is equals to 46 watt per meter per degree Celsius. Insulate rest of the surfaces. That is, we have to consider the thermal conductivity of copper rod as 386 watt per meter per degree Celsius. The thermal conductivity of steel rod is 46 watt per meter per degree Celsius. Also, we need to consider the surface area is well insulated from the non-conducting heat transfer material. Therefore, heat would only be transferred from the copper rod to the steel rod, and no other heat transfer would take place in the environment. Let's list out the given conditions first. Given the diameter of both rods, we have denoted it by D, is 3 centimeter. To convert 3 centimeter in meters, we can write it as 0.03 meters. The length of the copper rod given as 75 centimeter. We have denoted it by XCU, that is length of copper rod. Length of steel rod is given by 125 centimeter, that is X steel, length of steel rod. The temperature at the end of copper rod is 100 degrees Celsius. So we have written as TCU, that is temperature of copper rod. Further, the temperature at the end of steel rod is 0 degrees Celsius. We have mentioned it as T steel, that is temperature of steel rod at one end. Also, the thermal conductivity of copper rod is given as 386 watt per meter per degree Celsius, that is denoted by KCU, that is thermal conductivity of copper rod. Also, the thermal conductivity of steel rod is given as 46 watt per meter per degree Celsius. We have denoted it by K steel, that is thermal conductivity of steel rod. What we need to find is temperature at the junction of two rods. Let us denote that as phi. Heat current passes through the system is I is equals to thermal conductivity of copper into area of cross section of copper rod into temperature at one end of the copper rod minus temperature at the junction of the copper and steel rod divided by the length of the copper rod. This would be is equals to thermal conductivity of steel rod multiplied by area of cross section of steel rod multiplied by temperature at the junction of steel and copper rod minus temperature at the end of steel rod divided by length of steel rod. As we can see that A is common in both the sides, and we also know from the given conditions that the diameter of both rods are same. Therefore, we can make out that the area of both rods would also be same. Thus, we are cancelling out area of cross section of copper rod and area of cross section of steel rod with each other right away. Thus, by putting values to this equation, we can write the thermal conductivity of copper rod as 386, the temperature at the one end of the copper rod as 100, the temperature we have to find out, that is the temperature at the junction, is equals to phi divided by the length of the copper rod, that is 75, is equals to 46, that is thermal conductivity of the steel, multiplied by phi, that is the temperature at the junction point of steel and copper rod, minus temperature of steel, that is 0 degrees Celsius. divided by the length of the steel rod, that is 125 meters. By simplifying this equation, we would get the result as phi is equals to 93 degree. So this is the answer of our question, that the heat current processed through the system is 93 degrees Celsius, or the heat current at the junction point of copper rod and steel rod is found out to be 93 degree Celsius. Thus, here we close our session 2.